Hi everyone. I'm Jamelle Serrano, or you can call me Shemaine. And today I'll be presenting my research paper on the use of the most recent machine learning algorithms to improve the efficiency of solar photovoltaic systems and why this is important for the Philippines, which is where I come from, and how the country can utilize these technologies. So, why solar energy? Why is this important? First, solar energy is a great renewable energy source since it collects energy from the sun, which we all are accessible to. Researchers predict that by 2027, solar energy will have surpassed coal, thus making it one of the largest energy renewable sources in the world. The Philippines has a growing demand for electricity and high solar radiance, so they are aiming to shift to renewable energy. Solar is especially promising our because of the Philippines' long exposure to sunlight. But despite this, in 2024, solar power only made up to 2.9% of the Philippines' electricity generation. This means that we are not taking full advantage of our potential. So here is a graph of the growth of solar generation systems in the Philippines. As you can see, right now the Philippines is at 2.9%. Okay, so next. Okay, so before I get into machine learning, I would like to explain what photovoltaic cells are. So photovoltaic cells utilizes the photovoltaic effect, which converts sunlight into electricity when light photons excite semiconductor material electrons. And then it generates an electric current, which is given to an electric source, which is usually lights or um, anything that needs electricity. But the downside of this is its efficiency depends on a lot of external factors, which include heat, shading, dust, cloudiness, and also long-term degradation, which include cracks and aging. So, while the Philippines has great solar potential, since it has solar radiance, performance is inconsistent and systems may degrade over time. So this is um, an, an image of a more detailed image of how photovoltaic systems work. So when the sunlight hits the solar panel, it excites the protons and electrons and makes them connect. And after they connect, it they create a electric current or an electric field that goes to the load or the light. So yeah, and usually they're made out of silicone, especially in the market. Usually solar panels are usually made out of either monocrystalline silicone or multicrystalline silicone. So next question is why machine learning? Machine learning is an emerging technology in this day and age since it is derived from AI, which a lot of societies use. Machine learning is also an algorithm that can learn from real data and adapt, unlike traditional physics-only models whose predictions do not account for rapid and long-term changes in weather conditions, since it is only a linear prediction. It can also detect complex patterns in weather and performance, predict failures, and adjust system parameters. So this makes it especially valuable in tropical countries like the Philippines, where typhoons come a multitude of times per year and where weather becomes extreme very quickly. So like right now, um, just sudden rainfall in the Philippines. So that's one example of how weather can change in an instant in the tropical areas. As for my purpose of study, my paper reviews the latest advancements in machine learning for photovoltaic systems and highlights the research gaps. Most studies are based on temperate climates like Europe and North America. Um, Through my research, I found that there is little focus on tropical regions such as the Philippines, which face very different challenges like high heat, and sudden cloudiness. So the paper aims to provide recommendations to address these issues. For my methodology, I conducted a literature review of studies from 2015 to 2025 to retain its credibility, and I used databases like Science Direct, IEEE, and MDPI, which are academic journals. Then I analyzed each study by its machine learning method, dataset, accuracy, and limitations. The main applications I focused on are these three factors, which are energy forecasting, fault detection, and degradation prediction. Going forward to energy forecasting, forecasting is crucial as it helps operators know in advance how much solar energy will be produced, and they will be able to manage it accordingly. For example, if they predict high energy demand for a city in the upcoming next days, they can reserve the adequate amount of energy to avoid unwanted blackouts. In one study by Salman et al., they explored and experimented on a hybrid model combining convolutional neural networks, which is a type of deep learning algorithm, especially designed for processing visual data like images and videos. CNNs, or convolutional neural networks, are widely used in computer vision tasks such as image recognition, object detection, image segmentation. They also used long short-term memory, which is a specialized type of recurrent neural network designed to learn and remember long-term dependencies in sequential data, such as text or time series. And lastly, they also use transformers, which is an electrical device that sets up the alternating current voltage from the solar inverter to a higher voltage suitable for transmission to the electrical grid, ensuring that it is efficient and the power delivery is stable. So this type of model achieved a very high accuracy with only 0.55% error. But but the researchers addressed that in tropical regions like the Philippines, rapid cloud shifts and sudden weather changes reduce the accuracy of these forecasting machine learning algorithms. So for my next, we have fault detection. So PV systems fail at different stages of their life cycle, from factory defects to cracks and shading issues. In cities that are dependent on solar energy, these issues are aimed to be highly avoided in order to maintain the energy demand of these societies. There are three kinds of faults in PV systems. Number one is infant faults, which occur during the early manufacturing or installation stages of PV systems. Next is midlife failures, which happen between 10 to 15 years of their life, and they include issues like shading, cracked cells, short circuits, faulty diodes, and disconnected modules. And lastly, there are wear out failures, which usually appear in the final stages of a PV system's life. In 2025, XLV and others and other authors developed another hybrid model that combines thermal imaging with fuzzy logic, which is a reasoning approach within artificial intelligence that handles vagueness and uncertainty by using degrees of truth instead of binary true or false. In the context of machine learning, fuzzy logic can model human-like decision making and extract linguistic rules, sorry, from data. Sorry, sorry. Okay. Allowing systems to manage im- imprecise inputs and provide more nuanced, understandable outputs than traditional logic allows them to do so. And this combination detects midlife failures. This hybrid model reached a 90%, 98.85% accuracy in detecting faults. However, the authors note that this was only tested only under narrow conditions and not yet on large-scale tropical PV systems. Next is degradation prediction, which focuses on long-term um, wear like cracks, corrosion, or discoloration. In a paper by Dipanshu and others, they created a hybrid model combining artificial neural network, which is a type of machine learning model that is inspired by the structure and function of the human brain. They consist of interconnected nodes or neurons that process data through mathematical calculations, with their connections adjusted during training to optimize performance on tasks like pattern recognition, prediction, and classification. Another factor of the hybrid model is the random forest, which is an ensemble method that constructs a forest of many individual decision trees and combines their predictions to improve accuracy and robustness. And lastly is the extreme gradient boosting, or XGBoost, which is an ensemble learning technique that builds a strong predictive model by combining the predictions of multiple weak learners, typically decision trees, in a sequential manner. And this kind of model achieved an excellent accuracy of 0.96 R squared. Still, the authors emphasize the need to test this on more diverse tropical datasets for better real-world adaptability. So, moving on to summary of findings. To summarize, forecasting models are accurate but unstable in tropical weather. Fault detection models are powerful but not yet scaled. Diffusion models are accurate but not generalizable. So therefore, the common issue is a lack of tropical specific datasets. For my limitations and recommendations, the main limitations are most studies use data from temperate regions. Next, there is a lack of open tropical photovoltaic datasets. And lastly, there is an over-reliance on black box ML models. Black box ML models is a machine learning model whose internal decision-making process is opaque and cannot be easily understood by humans. Therefore, I recommend creating and building a tropical dataset in for tropical regions like the Philippines. Second, I recommend using transfer learning, which is a machine learning approach in which a model is built for one task is adapted for use of a different but related task, rather than starting training from zero. It makes use of pre-trained models, allowing for reduced training time, lower data needs, and fewer computational resources. This method is especially valuable in deep learning, where training large-scale models can be highly demanding. Lastly, I recommend combining physics-based um, and machine learning approaches for more reliable predictions. So putting the best of both worlds together would create more accurate and stable algorithms. And lastly, for my conclusion, through my research, I understood that machine learning has the potential to significantly improve solar photovoltaic efficiency by making systems more adaptable and predictive. But for the Philippines to fully benefit, future research must develop tropical focused datasets and models. And this will help maximize the Philippines' solar potential, cut off fuel dependence, and accelerate its clean energy transition. For my acknowledgements, I would like to say thank you to my mentor, Dr. Adarsh Ravi, for giving me the guidance and support on how to conduct and write my research paper. I personally appreciated our meetings as I learned a lot from them. Again, thank you, Dr. Ravi, for making my research experience better, and I will definitely never forget the advices you have given me. And as for the TSI Summer Institute, thank you for giving me this chance to conduct and present my research and giving me resources to foster my passion for engineering. So thank you guys. Thank you for listening.